Sometime in the next few years, the AI that's drafting your emails, generating your code, or rendering complex models, it might not be powered by the public power grid outside your window.
Right, the sprawling, vulnerable grid we all rely on.
Exactly. Instead, that server processing your request could be pulling its electricity from, well, a factory-built pocket-sized nuclear reactor sitting just a few yards away.
Yeah, it's a wild concept to wrap your head around.
It really is. I mean, we are talking about dedicated modular nuclear power humming away right next to the server racks. So today, our mission in this deep dive is to explore exactly why big tech is suddenly abandoning traditional power grids.
Yeah, we have a fantastic source for this.
Yeah, we are unpacking an incredibly detailed 2026 analysis. It's titled Deployment of SMR Nuclear Reactors for Data Centers 2026-2035. So, okay, let's unpack this, because the sheer scale of the energy crisis forcing this shift is, well, it's just difficult to overstate.
It really is.
I mean, according to the data, AI data centers are on track to consume tens of gigawatts of new electricity demand in the U.S. alone over the next decade.
Tens of gigawatts. It is a staggering surge in demand. And what the 2026 analysis makes really clear is that this isn't just about needing more power.
Right.
It's about needing a very specific type of power. Our existing energy infrastructure is fundamentally mismatched with the actual physics of artificial intelligence.
Mismatched because, I mean, we have solar, we have wind.
Sure, you look at the current toolkit, right? Renewables like wind and solar, they are the backbone of most corporate climate pledges. But data centers don't just need total megawatts over a year. They need absolute grid inertia and unwavering baseload stability.
Because AI training never stops.
Exactly. AI training models require 99.999% uptime. You cannot run a gigawatt-scale AI training cluster on a grid that fluctuates when, a weather pattern shifts.
Yeah, I like to think of it like trying to boil a huge pot of water by randomly turning your stove on and off. You need constant, firm heat.
That's a perfect analogy.
Right, because any drop in voltage can completely corrupt a massive training run. And those runs cost millions of dollars a day to operate.
Yeah, the financial risk is huge. So renewables physically cannot provide that firm, uninterrupted synthetic inertia at this scale. Not on their own.
Which naturally leads people to think about natural gas.
Right, which can technically provide that baseline stability.
But, I mean, burning gigawatts of gas directly violates the carbon-negative pledges these tech giants have publicly staked their entire reputations on.
Exactly, so they are boxed in, which leaves traditional nuclear power.
But wait, traditional nuclear plants take, 15 years to build?
15 years, yeah, and billions of dollars in cost overruns usually.
And Silicon Valley operates in financial quarters and, 18-month chip cycles?
They simply cannot wait for a traditional light water reactor to be constructed from scratch in an empty field. The AI industry's timeline and the traditional utility timeline they're just entirely incompatible.
So this is why we're seeing this massive pivot to the topic of the hour, right?
Yes, that is exactly why we are seeing this aggressive pivot to SMRs, which stands for small modular reactors.
Let's define what that actually means, because I think people hear nuclear and they picture those giant concrete cooling towers.
Right, the Simpsons intro. To understand why this technology is stepping up to fill the void, we have to look at the underlying mechanics. These are still fission reactors, but they are designed to generate under 300 megawatts electric, or MW.
Okay, 300 megawatts.
Yeah, and some of the microreactors generate much less than that. But the defining revolution here isn't just their physical footprint, it is the manufacturing process.
Because traditional nuclear plants are essentially bespoke mega projects, right? Every piece of rebar, every yard of concrete, every valve, it's custom engineered on site.
Exactly. SMRs flip that paradigm entirely. They're factory built.
Like on an assembly line.
Literally on an assembly line.
Yeah.
The reactor core, the cooling systems, the containment vessels, they are all constructed as standardized modules in a controlled manufacturing environment.
Wow.
And then once they're completed, they're loaded onto standard heavy-haul trucks or rail cars, transported to the data center site, and basically snapped together.
So you are shifting nuclear power from a heavy construction industry to a manufacturing industry.
Precisely.
And beyond the manufacturing speed, the source highlights a logistical advantage that seems to solve the absolute biggest headache in tech right now, which is transmission bottlenecks.
Yes, the grid itself is the bottleneck.
Right. The analysis focuses really heavily on what they call behind-the-meter colocation. Given how saturated our public grids are, bypassing the grid entirely seems like the only way these companies can actually scale up.
That is perhaps the most critical driver behind this entire movement. If you want to build a gigawatt-scale data center today and just plug it into the traditional grid, you are looking at a multi-year waiting list just for the interconnect queue.
Just to get permission to plug in.
Yeah. The physical wires, the substations, the transformers on the public grid, they simply cannot handle that kind of localized draw without massive, slow-moving upgrades.
Right. The grid wasn't built to suddenly power a small city in the middle of nowhere.
Exactly. So behind-the-meter colocation means the tech company places the SMR directly on their campus. The electricity flows straight from the reactor to the servers.
You bypass the regional transmission organization.
Yep.
You bypass the public utility queue.
Exactly.
And you bypass the aging public grid entirely.
Which is huge for these companies.
Here's where it gets really interesting, though, because knowing that SMRs theoretically solve the physical and logistical problems of AI is one thing. But looking at how these companies are actually acting in 2025 and 2026 shows a total transformation in tech capital.
Oh, absolutely.
The hyperscalers, Microsoft, Google, Amazon, Meta, they aren't just signing passive agreements to buy power down the road. They have become the primary financiers of advanced nuclear engineering.
They really have. They are taking on first-of-a-kind financial risks to force this technology into reality.
First of a kind. FO, right.
Right, FOK. It is a profound capital shift. Because historically, the nuclear learning curve has been entirely dependent on government subsidies and national laboratories.
Which inherently move at a very cautious, bureaucratic pace.
Exactly. Today, the urgency of the AI arms race is acting as an accelerant. It's pulling commercial deployment timelines forward by years.
And what is really striking in this analysis is that these tech giants aren't all placing the same bet. They are taking entirely different engineering pathways based on, their risk tolerance and their specific timeline.
They're hedging in very different ways.
Right. Let's look at Microsoft. They signed a 20-year power purchase agreement for 835 megawatts to literally restart Unit 1 at 3 Mile Island by 2027.
Yeah, the fastest route possible.
Right. They are choosing the path of least resistance, waking up an existing licensed traditional water-cooled plant because it is the absolute fastest route to firm, clean power.
It is a highly pragmatic, short-term play by Microsoft. But then when you look at Google or Alphabet, they are making a much longer-term bet on next-generation physics. Well, they signed a master agreement with Kairos Power to deploy up to 500 megawatts by 2030. And Kairos is not using traditional water cooling. They are building fluoride salt reactors.
Okay, let's drill into that for a second. Why jump to experimental fluoride salt when water-cooled reactors have, a 70-year track record? What is the actual mechanical advantage for a data center?
It comes down to pressure and safety margins. So traditional light water reactors require massive amounts of pressure to keep the water from boiling away at high temperatures.
Right, which is why they need those giant reinforced concrete containment domes we were talking about earlier.
Exactly. Fluoride salt, on the other hand, remains in a liquid state at extremely high temperatures without needing high pressure. It can natively absorb a massive amount of heat.
Oh, I see.
Because the system isn't highly pressurized, the physical containment structures can be drastically smaller, cheaper, and placed much closer to the servers.
So Google is betting on low-pressure salt for 2030, while Amazon is going in a completely different direction in Washington state.
Right? They have a very different approach.
Yeah, Amazon is heavily backing X-energy, aiming for 960 megawatts across 12 modular units. But X-energy uses high-temperature gas cooling. Specifically, they use helium.
Helium, yes.
I assume helium offers a different set of thermal advantages.
It does. Helium is an inert gas, meaning it doesn't become radioactive as it passes through the reactor core, and it is incredibly efficient at transferring high-grade heat.
Okay, that makes sense.
X-energy pairs that helium coolant with specialized spherical fuel pebbles that are practically meltdown-proof by design.
And Amazon is also hedging their bets, right? They're striking traditional utility deals with Talon Energy and Dominion.
Yes, they are covering all their bases.
Meanwhile, you've got Meta building an ambitious portfolio that includes TerraPower and a planned 1.2 gigawatt campus in Ohio with Oklo.
Everyone is making their moves.
Which brings us to the July 2026 announcement that really anchors this analysis. And honestly, it's the one that requires some serious scrutiny.
Druzo announcement.
Yeah. A company called Crusoe partnered with HALEU Atomics to build the world's very first nuclear-powered AI data center at the Idaho National Lab, and they're aiming for commercial operation in 2027.
It's an incredibly aggressive timeline.
Right, and hold on. I have to push back on this timeline for the listener. Reaching criticality with a tiny test reactor in a heavily subsidized, unregulated government sandbox is one thing.
Sure.
Putting a commercial reactor next to a data center in a zone governed by local NIMBY laws and commercial safety regulations is another universe entirely. Is 2027 actually a commercial reality, or is this just Silicon Valley PR meant to, boost stock prices?
It is a valid challenge. I mean, the jump from a national laboratory to commercial deployment is historically where nuclear companies fail.
Exactly.
However, the analysis points to the specific architecture HALEU is using to justify that aggressive timeline. HALEU reached criticality with its test reactor in July 2026 after less than 8 months of construction.
Less than 8 months.
Yes, they achieved that speed because they aren't building a miniature version of a large plant. They are building what they call the HALEU pod.
And mechanically, how does the pod bypass the usual multi-year construction delays?
By modularizing at the microscale, the HALEU pod generates a total of 50 megawatts electric. But it does so by clustering 5 separate microreactors, each producing 10 megawatts.
So they gang them together.
Right. And more importantly, these are cooled by liquid sodium.
Ah, another new coolant.
Yeah, liquid sodium has exceptional heat transfer properties and, like the salt we talked about, operates at normal atmospheric pressure.
Okay.
By keeping the individual reactors incredibly small, essentially treating them like large appliances, they can be entirely manufactured off-site, shipped on standard flatbeds, and swapped out individually for refueling, while the other 4 keep the data center running.
Oh, wow. So you never actually lose power.
Exactly. What's fascinating here is that it is an architecture designed ground up for the modular demands of GPU clusters. The capital from big tech is just single-handedly forcing this nuclear learning curve to accelerate.
Well, given that heavy industrial focus, I want to pivot to the environmental reality.
A very important piece of the puzzle.
Right, because these tech companies are constantly touting their green credentials. But building out thousands of factory-made nuclear reactors requires mining uranium, pouring specialized concrete, forging heavy steel containment vessels.
It's a massive industrial effort.
Right. So given that massive industrial supply chain, how do the life cycle emissions actually pencil out against something like, say, offshore wind?
When you look at the hard data on life cycle emissions, which comprehensively calculates the uranium mining, the steel and concrete manufacturing, the operational life, and the eventual decommissioning, the numbers heavily favor advanced nuclear.
Really? How low are we talking?
SMRs sit at roughly 6 to 13 grams of CO2 equivalent per kilowatt hour.
6 to 13 grams. That is remarkably low.
It is entirely comparable to offshore wind. But where SMRs truly separate themselves is in their energy density.
You mean the physical space they take up?
Yes. The amount of physical land, concrete, and steel required to generate a gigawatt of nuclear power is a tiny fraction of what is required to build a gigawatt of wind or solar infrastructure.
Because solar requires massive fields of panels.
Right. When you factor in the land footprint, it isn't even a contest.
And there's another environmental and safety aspect detailed here regarding how these specific designs handle grid failures. The analysis discusses island mode and passive safety.
Yes, passive safety is a game changer.
If I'm understanding the physics correctly, this seems like a massive leap from the legacy plants we grew up hearing about.
It is a fundamental shift in safety engineering. Older nuclear plants relied on active safety systems.
Active meaning they need power to run the safety systems.
Exactly. Meaning if something went wrong, they needed external electrical power to run massive diesel generators, which then powered massive pumps to push cooling water over the core. If the backup power failed, you had a crisis.
Right.
Advanced SMRs utilize passive safety.
It's essentially the difference between a modern electronic smartwatch that dies the second the battery fails and a high-end automatic mechanical watch that winds itself just by the physical movement of your wrist.
I love that comparison.
Like if the power cuts out to an SMR, the safety systems don't require an external battery. The inherent laws of physics like gravity and natural thermal circulation take over to safely cool the core.
That analogy captures the engineering perfectly. Because the coolant, whether it is fluoride salt, helium gas, or liquid sodium, natively absorbs so much heat. Because the reactors are physically small, natural convection is sufficient to remove residual decay heat.
No external pumps required.
No external pumps. If we connect this to the bigger picture, that passive safety is what enables island mode. These AI data centers can function as entirely self-contained microgrids. They do not rely on the local city's grid for backup power or cooling.
Which is an incredible thought for you, the listener, to visualize. You are looking at a future where these massive digital fortresses, housing our most advanced AI models, are completely severed from the vulnerabilities of public infrastructure.
Without sufficient islands.
Exactly. They won't be impacted by rolling blackouts, winter storms, or transmission failures.
It is the ultimate realization of distributed, localized, high-resilience generation.
But let's ground this in reality. So what does this all mean? Because if the physics of passive safety are proven, and the life cycle emissions are comparable to wind, and the hyperscalers have billions in cash ready to deploy, why aren't these rolling off assembly lines today?
That is the big question.
Right. The analysis clearly states that while we have these ambitious pilot programs in 2026 and 2027, the true wave of large-scale commercial deployments isn't projected until the 2030 to 2035 window. Let's walk through the major bottlenecks holding this back, starting with the economics.
Okay, the primary economic hurdle is the gap between first-of-a-kind, or UC, and nth-of-a-kind, or ENT deployments.
Right, we mentioned F earlier.
Right now, every SMR being planned is a epoch project. They carry the immense burden of initial research, supply chain establishment, and bespoke licensing.
Because nobody has done it exactly this way before.
Exactly. Historically, the first time you build a new nuclear design, it goes over budget. The economic premise of SMRs, the promised 30 to 40% cost reduction, only materializes when you reach the NX stage.
Nth of a kind.
Yes. That is when factories are mass-producing identical modules, and economies of scale finally kick in. We are years away from true mass production.
It's the standard manufacturing curve. Building the prototype of a new electric vehicle costs hundreds of millions. But the 100,000th vehicle off the assembly line is highly profitable. Exactly. But even if you have the factory ready, you have to get past the regulatory bodies.
And that is the second massive bottleneck. The Nuclear Regulatory Commission in the U.S. and similar bodies globally, they have spent half a century optimizing their frameworks to license massive light water reactors.
Right.
When a company like Google or Amazon brings them a design for a molten salt or high-temperature gas microreactor, the regulators have to practically write a new rule book.
Because the old rules don't apply to liquid sodium or helium.
Exactly. Licensing these novel coolants requires verifying entirely new safety margins and materials science. It is an incredibly rigorous and therefore incredibly slow process.
Which brings us to the fuel itself, which I found to be one of the most critical vulnerabilities outlined in the source. You can't just throw standard uranium into a modern microreactor, right?
No, you cannot.
The analysis highlights a specific fuel called HALEU. Can you explain the mechanical difference between what powers a legacy plant and what these SMRs actually require?
This is a major physical constraint. Traditional light water reactors run on low-enriched uranium, which is enriched to roughly 3 to 5% of the fissile isotope U-235.
Okay, 3 to 5%.
Right. But to make SMRs economically viable, to keep the core physically small and allow it to run for a decade or more without needing to be refueled, many of these advanced designs require fuel enriched to between 10 and 19.75%.
Almost 20%.
Yes. That specific tier is called high-assay low-enriched uranium, or HALEU.
So they need a much higher density of the active isotope to compensate for the smaller size of the reactor.
Exactly. But the problem is industrial capacity. Currently, the global supply chain for enriching uranium to that specific 19.75% sweet spot is heavily constrained.
Constrained how?
Well, until very recently, it was largely monopolized by foreign state-owned enterprises. Building out domestic commercial enrichment facilities to produce thousands of tons of HALE is a massive, multi-billion-dollar infrastructure challenge of its own, and it is only just spinning up.
Wow.
Without a steady supply of HALE, the advanced SMR rollout stalls completely.
And even if you have the factories, the licenses, and the fuel, you still have to deal with the public.
Oh, yes. The social aspect.
Right, because passive safety mechanisms and natural circulation physics are great in a white paper. But for the average citizen living a mile away, the word nuclear still triggers deeply ingrained fears about waste and radiation.
Public perception cannot be engineered away. While the volume of high-level waste produced by SMRs is physically very small, the geopolitical and social reality of long-term geological storage remains unsolved in many regions. A tech giant might secure the land and the NRC license, But if the local municipality aggressively zones against the deployment or ties it up in environmental litigation, the project will die. Social license to operate is just as vital as the regulatory license.
Finally, the analysis touches on a fascinating technical challenge regarding the specific nature of AI computing. Because an AI data center does not consume power in a flat, predictable line, does it?
No, it does not. The base load requirement is high, but the dynamic spikes are severe.
Spikes, like when a new model starts training.
Exactly. When an AI company initiates a massive new model training run across tens of thousands of GPUs, the power draw surges violently.
And nuclear plants don't like surges?
No.
Yeah.
Traditional nuclear plants like to be turned on and left at 100% output for 18 months. They don't like sudden shifts. These new SMRs have to prove they can effectively load follow.
Load follow, meaning adjusting output on the fly.
Right. They must safely and rapidly scale their thermal output up and down to match the dynamic, erratic power spikes of AI training clusters, proving that mechanical flexibility is a major hurdle.
Well, this raises a really interesting timeline question. If mass commercialization of SMRs isn't truly viable until the mid-2030s, what happens between 2026 and 2032?
That is the million-dollar question.
Because the AI models aren't waiting. They need power today. Is there a scenario where short-term economics win out and tech companies just bridge the gap by deploying massive solar fields backed by lithium-ion battery farms and, I don't know, natural gas peaker plants?
This raises an important question about exactly that tension. That is the dominant tension in the energy sector right now. SMRs are the long game for a pristine, permanent solution.
Right.
But in the interim, 5 to 7 years, piecing together hybrid renewable grids with massive battery storage and carbon capture natural gas might be the only mathematically possible way to feed these data centers.
It's going to be messy.
The transition will likely be a chaotic mix of stopgap fossil fuels and pilot nuclear projects until the SMR supply chain really matures.
It is a race between the messy, immediate realities of today and the highly engineered infrastructure of tomorrow.
Perfectly said.
Synthesizing all of this, the analysis paints a very clear picture. The underlying physics of SMRs, whether we're talking liquid sodium, molten salt, or high-temperature gas, is sound.
It definitely is.
The demand from the AI sector is practically limitless, and the financial capital required to bridge the gap is being deployed at an unprecedented scale by the biggest companies on Earth.
Unprecedented is the right word.
If they can solve the HALEU enrichment bottleneck, navigate the regulatory maze, and survive the grueling first-of-a-kind economics, we are going to witness a total reimagining of global energy distribution.
We are tracking a fundamental inflection point. The hardware architectures and energy supply chains being aggressively funded over this next decade, they will dictate the ceiling of human technological capability for the next century.
But I want to leave you, the listener, with a final thought to chew on as we wrap this up. It's something not explicitly detailed in the source, but the inevitable, logical conclusion of everything we've just discussed.
Oh, this is a fun one.
If companies like Amazon, Google, Microsoft, and Meta successfully fund, build, and deploy their own private fleets of modular nuclear reactors over the next 10 years, they won't just control our data, our algorithms, and our communications.
Right.
They will become the outright owners of the most advanced high-density energy network on the planet. Think about the geopolitical and economic implications of that.
It's staggering.
In the 2030s, could a tech hyperscaler effectively become a private utility company? If a severe winter storm knocks out the public grid in your city, could you find your local hospital or municipality forced to buy emergency nuclear power back from the exact same company that hosts your email?
It is a fascinating and deeply complex paradigm shift. We are moving toward a reality where data and physical energy generation are completely vertically integrated.
The lines between a digital platform and foundational public infrastructure are just vanishing. It certainly makes you look at that server processing your AI prompt in a whole new light.
Absolutely.
We want to thank you for joining us on this deep dive. Keep questioning the infrastructure that powers your digital world because, as the data shows, the old models are breaking and the physical landscape of the internet is shifting faster than ever. We'll see you next time.